Everyone has a different purpose in life. For some, it's providing for their family. For others, it's getting a sick-ass job to buy sick-ass things. For me, it's to watch one group of scientists beat the scientific wheels off of another group of scientists. Now, to be fair, this happens all the time. And it's the point of science. The point of science is to challenge other ideas in order to improve the understanding of a certain field. And that's a good thing. But sometimes the scientific beatdown feels extra sweet. For example, when a single research group beats up on the same concept not once, not twice, but 3 times. And that's exactly what happened in this paper called The Pathways for Nanoparticle Transport Across Tumor Endothelium. It looks to explain how certain types of cancer treatments, specifically treatments made of nanoparticles, actually enter cells. It's the newest paper from the Warren Chan lab at the University of Toronto that looks to completely dismantle everything that we previously thought about cancer treating nanoparticles. Now, I've already made videos on their 2 previous papers on this topic and gave them some of the most unbelievable scientific suck you've ever seen. And you should definitely check those out if you haven't already. But this one might be their Mona Lisa, where they try and answer the question, do we finally know how anti-cancer drugs get into cancer?
Science that's cool, papers so unique.
Welcome back to
Coolest papers that I read this week.
If you're new to the channel, welcome. Thanks for stopping by. If you're returning to the channel, welcome back. Thanks for stopping by again. I'd like to introduce a few concepts that are essential to understanding this paper. First of all, we won't be talking about all types of anti-cancer drugs, just the ones that are made from nanoparticles. For some background, nanoparticle-based drugs have been used over the last few decades because they've shown to reduce the side effects that are associated with traditional chemotherapy. We don't have to get into how or why just yet, but just know that early examples of nanoparticle-based drugs reduced life-threatening side effects such as cardiotoxicity by up to 50%. So for the rest of this video, just think nanoparticles kill cancer, which is good. The problem is that since then, nanoparticle-based cancer treatments have been very hit or miss, with only about 9 being approved since the late 1900s. And this is where the Warren Chan lab really focuses their efforts. A meta-analysis that they did previously showed that less than 1% of nanoparticles that are administered to people actually get to the cancer. So naturally, we want to answer the question, why? And this is where we get to my favorite part of every video on this topic. Shitting on the EPR effect. If you're new here, again, welcome. Thank you for stopping by. If you're returning here, welcome back. It's time to shit on the EPR effect. The enhanced permeability and retention effect, also known as the EPR effect, is this controversial concept in the field of anti-cancer drug delivery by which molecules of certain sizes, typically nanoparticles and slightly larger drugs than normal, tend to accumulate in tumor tissue much more than they do in normal tissues. In my previous video, we discussed how the EPR effect is the theory that describes how nanoparticles leave the blood and enter cancer tissue. This theory suggests that nanoparticles enter passively, or that they just fit between these really big spaces between the cells that line your blood vessels. Specifically, the blood vessels that surround the cancer and that were grown really, really fast because the cancer grows really, really fast. These special blood vessel cells are called endothelial cells. They're the cells that make blood vessels nice and sturdy, but they also act as a gatekeeper between your blood and your various tissues. Remember this word because you're going to hear it a lot throughout this video. The EPR effect claims that these endothelial cells are like a really terrible keeper in footy. Just holes everywhere. Doesn't take much to get past them. The Chan lab's already provided a ton of evidence as to why this probably isn't the case. They've previously used something called the zombie model, cool last name, to show that nanoparticles have to enter cancer actively, meaning that there's some energy consuming process that brings the nanoparticles into these endothelial cells and eventually through the other side and into the cancer tissue. This led the Chan lab to create something called the active transport and retention principle, also known as the ATR principle. Note the word active. This ain't no PTR principle, boy. The ATR principle basically says that these endothelial cells act like a little fairy. Anti-cancer nanoparticles enter the endothelium from the blood before shuttling them all the way into the cancer. But despite their incredibly cool and perfectly defined acronym, there were still a few questions they needed to answer, such as, how the fuck? They might have shown that nanoparticles enter actively in some way, but there are a lot of different ways that nanoparticles can do this. For example, this review claims that there are at least 6 different mechanisms that allow nanoparticles to get into cells. This general process is called endocytosis, which you Latin-speaking folks will know means to enter cells and stuff like that. And you might be thinking, we already know that one of these pathways works, so why do we care which one it is? As with most things in science, knowing the how and the why is more important than just knowing the what. If we can learn the how and the why, we can learn how to design nanoparticles that enter these endothelial cells much more efficiently, and eventually kill cancer cells much more efficiently. Maybe up to bump that number up a little bit. And this is why this paper excites me so much. The field of anti-cancer drug delivery is absolutely starving for good news. These types of nanotechnology started out so hot, but have basically gone nowhere in the last few decades. And as someone who spent more than half a decade working in anti-cancer nanoparticles, it's fascinating when people who are way smarter than me can make really important advancements in the field. And boy, does this paper ever advance. The Chan Lab wanted to answer the following questions. Which is the main pathway that allows nanoparticles to actively enter endothelial cells and through to the cancer tissue? And do different nanoparticles use different pathways? Let's get it. Remember when we showed this absolute clusterfuck of a diagram that showed the different ways that nanoparticles can enter endothelial cells? Luckily, the lovely people at the Chan Lab don't want to torture us with looking at all of the different pathways, so they just focused on 3. These 3 pathways are calveoli, clathrin, and macropinocytosis. Big words, yes, but very important, and we'll hear them a lot, so you'll get used to them. They all have the same general function and end goal, which is to take in nanoparticles that are in the blood in the form of vesicles. These are basically little pockets that hold on to nanoparticles. But as we mentioned before, the details are very important for actually determining how nanoparticles enter cancer tissue. For example, the calveoli and clathrin pathways both require nanoparticles to bind to a receptor that is sticking out of the endothelial cell. It's like you need a specific key to enter your house. No key means no house, means no Fortnite. Macropinocytosis, however, is known as cell drinking. No receptors are required for drinking. The cell membrane just changes its shape and it's able to engulf the nanoparticles and bring them into the endothelial cells. No key needed. Your house just knows when you need to rip Fortnite with the boys and will let you in whenever you need to. More importantly, these different pathways form different sized vesicles. Vesicles from calveoli are the smallest, ranging from 60 to 80 nanometers. Clathrin vesicles are slightly bigger, around 100 to 150 nanometers. But macropinocytosis vesicles are much bigger, known to be above 200 nanometers in size. These numbers are incredibly important because nanoparticles for treating cancer come in a whole array of different shapes and sizes. And obviously, not every nanoparticle size physically fits into each of these vesicles. The Chan Lab put these different pathways to the test by injecting nanoparticles into mice that had cancer. They also injected different compounds that would block certain pathways from taking up these nanoparticles. Finally, they removed the cancer from each mouse and took these really detailed pictures with a really high-powered microscope. From here, they could count how many nanoparticles could enter the endothelial cells in these endothelial vesicles, but what they saw was really surprising. For example, here's what happened when they blocked off the macropinocytosis pathway. Only about 17% of nanoparticles enter these endothelial cells, which is about 8% less than when macropinocytosis was available. Shockingly, it seemed like the calveoli and clathrin pathways also played a very significant role in bringing in these nanoparticles. Clathrin and calveoli decreased nanoparticle entry by 19 and 9% respectively, which almost makes it seem like macropinocytosis is kind of trash. Like, it wouldn't even be that big of a deal if we never had macropinocytosis ever again, because nanoparticles could just enter cells through the other 2 pathways. But this is only part of the story. What these numbers don't show is how many of these nanoparticles pass through the endothelial cells and into the cancer tissue. Because when we see this, things change a lot. When they blocked off macropinocytosis, they saw about 31% fewer nanoparticles in the cancer tissue compared to a regular cancer. When they blocked off calveoli and clathrin pathways, they saw no significant difference in the number of nanoparticles that got into cancer. So what do all these dots tell us? All 3 pathways play a big part in how nanoparticles enter these endothelial cells. But once in these cells, the pathway even biggerly determines whether they're able to go through the cells and into the cancer. And remember, we can't kill cancer unless the endothelial cells allow the nanoparticles to get in there. And here's my trash analogy. You ever go to a party and start talking to someone that seems really friendly and welcoming at first, but then like 20 minutes later, you don't want anything to do with them and you just want to leave the conversation, but they won't stop yapping and you can't escape this convo? Yeah, that's what clathrin and calveoli pathways are like. Meanwhile, you have macropinocytosis. They're just as welcoming as the other guy, but they'll gladly let you leave and enjoy other conversation in other rooms of the party, if that makes sense. Now, it's important to note that all of the experiments done up until this point used nanoparticles of a very particular size and shape. There was very little diversity in the nanoparticles that they used, which brings up question number 2. Different nanoparticles used different pathways to enter these endothelial cells. They performed the same experiment where they took really detailed pictures of mice cancers after injecting these nanoparticles to see where the nanoparticles went. But instead of using the normal 50 nanometer nanoparticles, they compared really small 15 nanometer nanoparticles to relatively large 100 nanometer nanoparticles. And then they measured to see which of the pathways are being used by measuring how big the vesicles were. These are both pictures of the big 100 nanometer particles. On the left, we see a big vesicle that holds 2 separate nanoparticles. Big vesicle, means big dog, macropinocytosis. But look at the right. One big nanoparticle inside a little vesicle. This unique little furball probably entered these tissues through the clathrin pathway. Now, this probably wasn't ideal for this nanoparticle because he kind of looks like me trying to squeeze into my pants after a really juicy Thanksgiving feast. But either way, we can tell that these nanoparticles used two different pathways. But how did this look with the smaller nanoparticles? As you can see here, the small 15 nanometer particles were pretty evenly split between using macropinocytosis in purple versus either clathrin or caveoli in gray. Now, the split was about 60 to 40% in favor of macropinocytosis. But things were very different when we used the thick boys. More than 80% of these 100 nanometer particles were using macropinocytosis. Now, because we're all super duper smart and super duper handsome, this probably isn't all that surprising to you. Small nanoparticles can use the pathways that have either big or small vesicles. Big nanoparticles, however, mostly use the pathway that has big vesicles because, well, they're just more comfortable in there. If you're hopping on a transatlantic flight, wouldn't you rather dress in baggy sweatpants than a leather leotard? Please don't say the leotard. So what does this all mean? This tells us that the mechanism of how nanoparticles enter endothelial cells, and eventually cancer tissue, is greatly dictated by the size of the nanoparticle. The larger the size, the more likely that our boy macropinocytosis is being used. As a side note, they also tested nanoparticles made with different materials on the outside and saw basically no difference. This is really important to us nanoparticle nerds. Assuming that entering cancer tissue from the blood is our #1 priority, this means that we can spend less time worrying about what the nanoparticle is made of and more time on adjusting the size. Now, I'd like to leave you with a couple other things before I head on out and gush about other nanoparticle things that nobody really cares about. The first is this delicious diagram that outlines everything that we learned in this paper. If you had a hard time following along with my stupid sizes, this should sure things up for you. On the left, we see how endothelial cells near cancer use macropinocytosis to bring nanoparticles into these gatekeeping cells. These particles travel through these cells and shoot out into the cancer tissue, giving the nanoparticles a chance to kill the harmful cancer tissue. On the right, we see that this process happens a lot less around healthy tissue. I'm oversimplifying it a bit because the authors state that a healthy spleen and a healthy liver are still very efficient at taking in nanoparticles, but that's a whole ass rant for another day. More importantly, I'd like to leave you with the thoughts of the first author of this paper, Jamie Wu, and see what she thinks of her immaculate work. The findings in this study are important because they tell us how the cell and molecular mechanisms of nanoparticle tumor entry. Now we can visualize the process. We build on the knowledge that nanoparticles cross tumor endothelial cells to get inside tumors by figuring out the how. I think about it as identifying the right knobs on a control panel so that we can tune and enhance nanoparticle delivery. Probably better than my stupid little house key examples. Knowing the pathways teaches how to manipulate them for applications. For example, if we want to boost macropinocytosis, what might be the signals inside and outside of the cells that actuate this behavior? If we want to boost the receptor-based pathways, which currently plays a very small role, but could mean that this is a huge unexploited opportunity, what receptors on the tumor endothelial cells should we target? So you can see there's a lot more follow-up questions we are excited to explore. I love it when curious scientists want to do more stuff. Good on ya. Since I started my PhD, I kept wondering why the phenomenon of EPR exists. If it's not because of gaps, as we began to learn, what's special about the tumor? For Jamie, it was satisfying to find an answer to this question. AKA that the tumor is special because it has upregulated nutrient intake processes such as macropinocytosis, which makes sense in the context of tumor biology, since cancer cells need to eat to grow, and the tumor endothelial cells feed them by bringing things in from the blood. So this study was fun because the answer was both unexpected and perfectly logical. And I love that take, something that is unexpected and perfectly logical. Like the EPR effect always says, oh, tumors are really hungry, that's why they take in more nanoparticles. But they thought it was because they were so hungry that they were built improperly, and so the spaces between the cells allows nanoparticles to go through. But Jamie and the crew already showed that each cell is eating the nanoparticle and then bringing it into the cancer tissue. So, different way of things working, which is really exciting. I think that nuance is really important in how we can design nanoparticles in the future. And on that note, this gives us nanoparticleologists a very important look into how nanoparticles should be designed in the future. We can design nanoparticles that can use this pathway much more efficiently, ultimately getting more cancer-killing nanoparticles into the cancer and saving more lives. So thank you very much, Jamie, for your insights and your unbelievable work. Really, I could not thank you enough for giving me such a great read. And thank you to the whole Chan Lab. They're always sliding in my DMs, giving me really fun things to talk about, especially Stefan and Shrey. Thank you for getting just as hyped as I am about nanoparticles. I'm genuinely really grateful for all of you helping me out in this process. But I'd also like to thank all of you for watching this and watching me yap about nanoparticles for way longer than I needed to. Seriously, I don't think anyone would click on this or any one of my other videos. So if you're here watching, genuinely from the bottom of my heart, Thank you for watching. Now, if you'd like to continue watching me yap, please like and subscribe, and let me know in the comments on other things you'd like me to talk about. Don't be shy to suggest other cool ass papers, and feel free to follow me at MattyCPhD on all socials. I'm most active on Instagram, where I do Q&As, share little bits of my life, and give you content like this, but in bite-sized form. Now that's all for today. See you later, nerds!